Okay. I wanted to also work on like the board though, but okay.
You just do board behind you. That should be okay.
Yeah, hope it's fine. So should I just start? Okay, today I'll talk about SuperSpartan and its extension of a protocol called Spartan, which is proving scheme for R1CS. So let's go started with R1CS a bit. So the R1CS is about proving AZ BZ is equals to CZ, where any program can be converted to this A matrix and D matrix, and Z, which is witness. Oh, sorry. This one. So yeah, so any like program could be converted to A, B, C metrics, and Z will be consist of like Z, I mean, witness, also known as a trace, execution trace. So yeah, the constraint actually comes down to like AZ, BZ minus CZ is 0. So in SuperSpartan, they make another constraint system called customizable constraint system. So here let's define the R1CS first. So given the size bounds Mn, capital N, and L, there is 3 matrix of dimensions M times N with at most N non-zero entries. So it's called sparse matrix also. So if most of the matrix is 0, then it's a sparse matrix. So given that, and there's a public input X, so which is of size L, and the witness is the size Fn minus L minus 1, so that Z is actually X concatenated with omega like this. So we just want this to be size N. So witness is just the rest of the front part of the Z vector. And so given these, we want the program comes to this constraint. So in customizable constraint system, we have a bit more parameters. Looks complicated, but it's not that complicated actually. So in here we have only 3 metrics. In here we have T metrics, number of T. So we have another T here. So size bound T, which is number of metrics. And there is Q, which is Q multisets. So basically for R1CS, this is, for example, one of the multiset. So for example, S0 will consist of 0 and 1, so that it will multiply 0 and 1. And S1 will be maybe only 2, so that it will consist of M2 only, right? So we want this to be like M0 times M1 minus M2. So this is like go to different subsets. Okay. So I'll also get into it on the board. And
so number of S is 2 and number of M is 3 for RCS case?
Yes. So there's also constants for corresponding to each multiset. So for example, CZ has -1 coefficient here, right? So C1 is going to be like -1. C0 is going to be just 1, basically. So yeah, so to sum up, we will just sum all these matrices. So when we this is just a complicated expression for saying like we will sum up all the matrices in a multiset and then multiply them by the coefficient and sum them up. and it should be 0. Okay. So this is just element-wise product. So it is like AZ. We will calculate AZ. It's going to be a vector of n size, and this is going to be also a vector of n size. And this is multiplying element-wise of that vector. So yeah, so this is a big complex constraint structure, constraint system that can be converted to R1CS or Plonkish. Yep.
No, sorry. You can go. Sorry.
Or Plonkish or air. So I don't want to get into Plonkish because I'm also not that knowledgeable in Plonkish. So in air constraint is, I guess, more easy to grasp than R1CS. So air constraint actually has like one transition state. So it is also like used in like ZKVMs. Like, so we have one state transition polynomial or function, you can say, that constrains how the state should be transited, right? Per execution cycle. And so we have also another constraint that G is just Q monomials. I'll get into it later. I'll like explain more in detail what these monomial mean and what D means. So the air constraint is the weakness. We can write like this. So X is public input, and so first half of X is public like input, you can say, and in air constraint, and then the last half is the output. So in execution trace, we want the first row to be the input of the program, and then the last row to be output of the program, right? So the input is public, output is public. The trace is kind of hidden. If you want ZK, it's hidden, but like, yeah, just not really important for the verifier. And then what we want is for all rows, we want this state transition function to hold, which is like just 0, right? So it will take in the previous state and then the next state, and then it should evaluate to 0 for all rows. So in some complicated case, we can have multiple Gs. In this case, we will just give one random from the verifier, and then the approver can just random linear combine this multiple state transition functions and then make one state transition. And it's also, you can just use 1G here.
Question. So basically, there is a CCS.
Yeah.
I forgot about example.
Yeah.
CCS. Then we can, if we represent the polynomial to CCS, then it can be represented to the error too.
Yes. So
what's the reason for using CCS then?
So actually, CCS is more diverse. So R1CS can become CCS, can be represented with CCS, and air can be also represented with CCS. So CCS is like a how to say, it's more recently introduced new way to make a constraint system that can be. So if you can make a proving scheme for CCS, it can prove air, it can prove R1CS, it can prove Plonkish. So previously we had to have like snarks for air and snarks for like R1CS separately because they are different in nature. So CCS is basically unifying them into one generic constraint system. So you can say.
Is it also, can we view it like, so Spartan or SuperSpartan is a proving scheme that when it has a benefit if the matrices are sparse case, and R1CS is, so Spartan is for R1CS and SuperSpartan is for CCS, and CCS also is a sparsity. That's why we wanted to convert it to CCS.
Kinda. Yeah, but like I guess it is just so this is SuperSpartan and is actually so Spartan cannot be applied to air. Now SuperSpartan applies makes it possible to apply to air, basically. So now you can apply the Spartan to air or R1CS. Previously, in the original original Spartan, it wasn't possible. So by making all into just basically sum of matrix and vector multiplication, it is making Spartan can be applied to all systems. So for now, so we can just sum up to get back to it, we can just sum up all the state transition functions and then make one G. And obviously, if this was 0, the sum will be also 0, right? So we can do the same check. We will just check the G is 0 for all row. And so I'll explain how actually. So in CCS, we have a bunch of metrics, but now here we have one polynomial, right? So I'll also get into how we convert this polynomial into a bunch of like metrics, M0 to MT minus 1. So how to start? Okay, so I'll stream the board. Hope you can see. Here is the last one. So I guess R1CS case was clear, or should I? Do you want me to explain? I mean, I'm fine.
Can you?
Yeah.
Sorry.
No, I mean, it's fine. So as we said, there's ABC. ABC and Z vector, right? This is actually witness 1, and then this is public input output, right? And then, so this is basically, you can say M0, this is M1, and this is M2. And yeah, Z is same for the R1CS, I mean CCS, Z is same. And then S0 is gonna be like 0, 1. S1 is gonna be 2. And then C0 is gonna be, because we want to represent AZ, BZ minus CZ equals 0. C0 is gonna be 1, and C1 is gonna be minus 1.
Should you actually use a different pen? It's kind of hard to see.
Yeah. Okay, this is much better. Minus 1. So the sum will be just like, so we will first multiply everything in subset, let's say 0, and then it's going to be like M0 times M0Z, M1Z, and then multiply by C0. So this is like 1 times this. And then we have sum over, right? So we will sum, and then we will do this next subset, which has only 2, so it's going to be M2Z. And we have coefficient minus 1, so it's going to be minus 1 here, so it's just going to be minus, right? Equals 0. So this is just special. R1CS is now just a special case for this customizable constraint system. And then now the air case, it's going to be a bit more complicated. Any questions, by the way? No? So the air case. So in the air, the Z is now a bit different, right? In R1CS, previously it was like witness 1x, but now we want this to be a bit different. It's gonna be like, I'll show it on the slide as well. Like, I think it's here. So it should, if I remember correctly, it's there. So first half of input is the starting, like, so it's, let's say, until t/2, and then witness, and then this is actually n-1 times t/2. So basically n-1 states basically. So our state in this constraint is t/2, you can say. So, and then the last half of x t. And then we have to fill in the matrix so that we have like nz.
Can I turn off this for a moment because it reflects, so
Oh.
in video it hard to see. It's better or 준범님
Maybe
어떠세요?
this side. Can we turn half of the side?
네.
Or?
괜찮아요. I'm fine.
Oh, nice worse.
Yeah, I cannot see. Oh, really? Okay, sorry.
So we want, like, for example, n0z, n1z, like, let's say, like the matrix is first row z plus, let's say, n1 first row z is like same as evaluating the state transition at the first row. So it's gonna be like x first, the input, right? And then witness is first to like, so this is gonna be like input and then the first state, right? After first executions, right? State after the first cycle, cycle. So we want like the matrix first row to represent this. So I'll get into like, so let's say our ZK, our like execution trace is trying to calculate just negation. Okay, we want to have like for negation. So it's gonna be like just our state is gonna be something like the input is gonna be like x0, and then the next is gonna be like minus x0, x0, minus x0. So very simple. So our z is gonna look like this, right? And then the output is. So after like for negation, what is gonna be output b? So it's, so this, in this case, the g is actually this. This is equivalent to g of the simple. This is gonna have because we have just one variable in each state, the g is gonna have two. So the input and output, right? So it's gonna have, let's say, x0, x1, and since it's just negation, it's gonna be sum of these two. It should be 0. So if you see g is always 0, if you take this 2 or this 2 or this 2, so this transition is always valid, right? So how do we express this g function like over here? So actually I have this mapping. In this case, it's very generic, so it's a bit hard to maybe understand, but I'll try to explain. Or, okay, first of all, so if you see from the equations, t is 2 because number of variables for the g is 2. So, and g function is just x0 plus x1, simple function. And let's say we have 5 state transitions. And then n will be like, actually, it should be size of the z, which is n plus 1 times t over 2, which is should be 6. So 6 times 1, right? T is 2, so it's going to be just 6 times 1, so it's 6. And actually, I will just write down the matrix. So m's are going to be like 5 times 6 matrix, right? So yeah, so I'll write it's going to be 0, 0, 0, 0, 1, 0. Then it's going to be 1, 1, 1, 1. So 6. So all zeros, right? So this is n0. We'll only have 2 matrices. So if we multiply by the states, let's say, actually in this case, in the CCS, we get like, we'll have, the witness is going to be a bit different. So we'll have, let's say we have this state, right? So this is at 0 cycle, 1 cycle, let's say it's S0. State at S2. So S6. No, it's 5. So actually the Z is going to be a bit different. It's going to be like S1, S2, S3, S4, S5, and then the public parts, S0. Actually, S5 should be after. Right? So this is public input, and this is the public output, and this is the witness part, the hidden part. So M0 times Z is going to be just what this is S0, the fifth one, right? So fifth one, and then what? There's 2. Okay.
Yes.
There's 2, and then there's 3, there's 4, there's 5. Yeah.
Here's the number 1 is missing. One is missing.
S2.
But I guess it should something like S0 to S5. It should be in order of S0 to S5. Next one should be S1 to.
The first one should be the public input.
But you should put it on. Put it the first.
Like
first.
this, you mean?
Yeah. So that what you want to show is that S0 plus S1 is 0, S1 plus S2
Yeah,
is 0.
that's true. So we have to have this output actually.
Yes.
And then, so the matrix should be a bit different. This is 1.
And then the diagonal shifted left 1.
I see. Okay.
And then you missed the fourth one on the next one.
So it should be shifted 1 down, right?
Yeah.
And then for the last one should be.
Like this?
Yes.
Yeah.
I see.
1,
And this is 0, 0, 0, 0,
0,
0, 1, 0, 0, 1.
And then this one, the last one should be 1. Because it's 5. That's 5.
Okay. This should be 1. And there should be 1 more 0 here.
Yeah, so
Oh, okay. There's another row.
Ugly, right?
There's another row.
there's another row.
Oh no.
No, there's 5.
I
5
see,
times
yeah.
6.
1, 2.
Right most covers.
And
Oh, you're right. You are missing a
Oh.
diagonal.
yeah,
Oh, wait.
sorry.
But there's 6 total variables on the right. And... Okay, that's right.
And I'll just fill in. Yeah.
No,
Okay.
You're missing one. You're missing one.
No.
Missing one row.
It's 5 times 6.
Wait, but you're missing
Fourth column one of them should be 1.
missing S.
Fourth column?
Fourth column. If you're counting from the first, second,
Yeah.
one of the rows should be 1. Otherwise,
You need another row. But it's a 5 by 6. How does that work? But the
Is
total number of
0
variables
S-
is 6, not 5.
S1,
Wait,
S2.
no. 2.
Yeah,
and
0,
6 by
0, 1.
0, 1.
Yeah.
You're doing
Yes.
6 by 6.
No, I guess I just have to remove one state then. I just have to remove one state.
Maybe
I put too much.
you don't need this one.
Yeah, I think
I think that one should have up to S5.
S4 and then S5.
S5, yeah, this one doesn't have to specify S5 here. Because S5 should be up here and
Yeah, that's true.
Did you get rid of the last row of the matrix? Okay, that looks like it should be right.
Okay.
actually should be 1. And it should be 0.
Wait, what?
Because no.
Wait, no, that's
No.
S5.
Oh, that's S5.
Yeah, that's-
Oh, so confused.
Yeah, sorry. I should have made.
Okay. Yeah, okay. I agree.
Cool.
Yeah, cool.
And then we want the other one to be like S1 to S4, right? S5.
Yeah, 5.
So if we sum this, it's gonna be like S0 plus S1, S1 plus S2, S2 plus
S3.
S3, and then the constraint is these all should be 0, right?
Makes sense.
Okay.
So we have to just construct M1 in a similar way, and then the M1Z is gonna be like this, right? So it's actually, if you follow the equation, you can actually get it. Yeah, so CCS is something like this. And then I have to get into now the hard part.
Is it
You
actually
didn't
super
start?
Spartan now?
Yeah, now I should get in how to prove this, right? So now we have a general constraint system for air and RCS, and now we have to prove, like make a proving scheme for this new constraint system, CCS. And so basically it is a generalization of Spartan. So I'll review Spartan again because it's been a long time. So in Spartan, what it uses is, okay, let's get it. So it uses sum check. So for sum check, it is, we want to check in sum over some, you sum this polynomial over some domain, and it should be, we want to prove that it's equals some t. And the sum check protocol, we can reduce it to evaluating g at some random r. So we won't actually calculate the sum. We will just evaluate g at random r, and it should be, so that's the high level view of sum check. And then we have a multilinear polynomial extension. Sounds kind of complicated, but so suppose we have this g function that maps like m word bit word, you can say, mu length bit word, you can say, maps this to a field. And then, and the polynomial extension is this mapping, this is converting this mapping from mapping to polynomial. So let's say, so what it means by mapping is like, so let's say how to make an example? So for example, let's say we have a F mapping and it has two inputs, and this outputs matrices X, I index. Then this is not actually a polynomial, and this is just a mapping. So, but we want to express it in a polynomial way. So it's in something like, we want it to be some X times K, something like this, right? Y or something. And then, so we want to convert this mapping to a polynomial, and that's called low degree extension. And then there's multilinear extension. So multilinear means that the degree of each, so this Z has these mu variables, and then degree of each of them is maximum 1 in each term. Kind of complicated, and we have also EQ extension, a lot of notation. So it is just basically equality. So if X is equals to E, then it gives you 1 and 0 otherwise. So a polynomial commitment scheme basically consists of 4 things: setup, commit, and then you can open this commitment at some point. So which means you want to check the evaluation of this polynomial at some point. So I'll get into the protocol. So as we mentioned in the R1CS, we have this 3 matrix, ABC, and there's Z vector, which consists of witness and public input output. So this matrix is actually a mapping, right? So this is a bit representation of the row index, and this is a bit representation of the column index. Then given this, the matrix entry will be filled. So this is, you can say this A matrix is mapping from this to a field, row index and column index to a field. And then what we want to do is we will convert this mapping to actually a polynomial for each ABC, right? So we want to represent these matrices as a polynomial. So here we will have like, we have the polynomial representation kind of. So actually, so we have this X. So this X is a row index, you can say, row index. So given row index, this row should be 0, right? So this is summing up all the column over the column. And then of this, and then summing over column of CZ, and then for the given row index, it should evaluate to 0. So basically, this R1CS has become this FIO at over all possible X, it should be 0. So for all X in this big representation of row index, FIO X is 0. So now we will, so this is, we will make a low degree extension. And then it's actually a fixed formula, you can say. So it is well-defined. It is just a form. You can just think there's a formula to convert this mapping to a polynomial. So we have this polynomial, and we want to check this polynomial is 0 over all possible X. And this is actually a complex task. You don't want to check for each one of them. So what we want to do is we will try summing up them. We will sum up over all the possible x and check if it's 0. But actually, this doesn't mean it's 0 everywhere. It can be like 1 and minus 1. The sum will be 0, right? But so we have to be careful about this. And in here we use this EQ extension, right? So we don't actually sum over this because this is risky. We actually multiply this polynomial with this EQ extension. So if you remember, EQ extension is 1 only if tau is same as x. So tau is equal to x. So what this means is, so if we sum over, what this means is, so we have this function over tau. Now it's kind of more complicated, but so instead of summing over x, we will introduce another variable tau, and then so for all tau, this is going to be different function, right? So we will sum up all these function, and we'll have this one function. So this is much larger function, polynomial than this FIO. So the property of this Q function is like, so if this tau is same as x, then this is same as just FIOX, right? Because this is just 1. So QIO is same as FIO over the x over this Boolean hypercube. This bit representation is called Boolean hypercube. And then QIO is 0 outside of this Boolean hypercube, because EQ is going to be 0, right? If tau is not the same as x. So basically, this QIO is 0 everywhere if AI is 0 everywhere. So now we have this.
So I think what's tau?
Tau?
Yeah.
You can say it's another variable, like another variable, something like x. Too many variables, right? So yeah, tau, and then
Also, it's like confused. So we are thinking of FIOX, and then now why tau introduced for what?
So we want to check if a very good question. Like we want to check if this sum. We want to check if all this FIOX is 0, like over this x Boolean hypercube. So to do this, what we want to do is, so for now, FIO can be 0 over this, but non-zero outside of this Boolean hypercube, right? So if it's if let's say if you evaluate x over some x that is not in here, then it can be non-zero. So which makes it harder to check. So we want to make it 0 over everything. So to do that, we just multiply by this. So this is basically, this is 0 if tau is outside of this domain. So this makes that this QIO kind of 0 everywhere. If it's 0 everywhere, it is very easy to check because you will just random check so at this point, Q is actually a function over Fs, so it is much larger. So this is like you can say binary fields as domain, and this F is like, let's say baby bear. It's gonna be 2 to the 31, so very large field. So this QIO, so if you check, this is like 2 to 31 times S large field. So very large field. Like let's say S is 4, then it means like it's 124, which is kind of close to already the bit security we want. And so if we check one number in this 2 to the power of 128, 24 numbers, possible numbers, and it's 0, it's very likely that it was 0 everywhere. That's the main idea. So yeah, we just want to check this random thing. And
Yeah, kind of, kind of.
so you can say, so currently the possible values is 0 and 1, right? But if it's like F, it means like it can go to 2 to the 31 actually, instead of 0 to 1. And if it's like, let's say 2, then it can be, it's actually fine to be non-zero for F. For F, it can be non-zero, but it should be 0 over this smaller one, like smaller domain.
So are we trying to find or translate FIO to QIO to ensure that it's a zero polynomial?
Yeah, so the problem is if we just random challenge FIO, because at this point, FIO is only 0 at the lower part and not necessarily 0 outside of this part, you can say. So we are making this QIO so that it's 0 also outside of this. And then we will just random check this QIO.
I think we shouldn't call this as zero polynomial, right? Because zero polynomial means you have a zero coefficients for all.
Yeah, it is.
But it can have a coefficient, but when you evaluate some certain point, it gives 0.
Yeah.
So there's a probability where it's not technically a true zero polynomial, but isn't it like, given that we're doing a single random challenge to QIO and ensuring it's 0 by like probability, it should be a zero polynomial?
No, I mean, it evaluates to 0 over Boolean hypercube.
Oh, okay.
It's not okay. I don't know. I mean,
So like outside the domain, it's not
we don't
zero.
care. We don't care.
Kind of confusing for like.
Maybe it depends on how you define zero polynomial. But I thought that zero polynomial is like polynomial that has a 0.
In the paper, actually, they say 0 polynomial.
Really?
Yeah, it's just for the Boolean hypercube, it's all values returns like 0, then it's 0 polynomial for
I
over
see.
Boolean hypercube.
And also this random sample is over not Boolean hypercube, but
Yeah, that's true. Yeah.
but then if it's not 0 polynomial, this random challenge will fail.
But for the QI, yeah, QIO is,
Yeah, what weren't we talking about QIO?
I mean, P.
Yeah.
Okay.
So it's a zero polynomial. It should be a zero polynomial for over the Boolean hypercube for like originally we wanted FIO to be over zero polynomial over the Boolean hypercube.
Yeah.
Right?
Yes.
FIO is 0 polynomial over the Boolean hypercube, but it can be non-zero outside of the Boolean hypercube.
Yes.
But QIO is 0 polynomial.
So zero polynomial inside the Boolean hypercube and for QIO, and then also
that's
zero.
FIO is.
Mm.
So FIO is 0 polynomial over the Boolean hypercube,
Yes.
and QIO is 0 polynomial for the field.
All the domain. Yeah.
Oh, okay.
So like for this, I think like the verifier wants to like check the all like possible like inputs for the Boolean hypercube, but it is like 2 over like 2 to the like mu. So it just turns to like sum check, and then if sum check runs like okay, but it can be like canceling each other. Like,
Because it's negative.
yeah, it can be. So it's just
They just
Yeah.
separate it.
Yeah, that's true.
introducing the
Okay, so QIO tau is sum over. Okay, the basic idea is that. And then there's a lot, but I don't think I have time, but then there's a lot of like these parts are just how to now perform this sum check. So, but overall, okay, what can I fit? So in the GIO, I mean, so this FIO is actually like these times this minus this. So if we denote this, we can just, this is also kind of a sum check, right? So this will reduce to evaluating this at random X. And then, yeah, actually, you can say this is just a bunch of, all these sum will be performed as a sum check, and then it will, so at the end, too much thing to cover. I didn't even start SuperSpartan, but
There is worst part of this. Okay.
so yeah, somehow now we can prove it. So the main idea, and then in SuperSpartan, it's actually again we will just we have these metrics, more metrics now, just and now the formula is just too complicated. But yeah, we have, so we had what, like a extension for each matrix, right? Polynomial representation of each matrix, and then we'll just instead of the Hadamard product, we will just use the polynomial product, and then we should evaluate to 0, and then it's also a sum check. Yeah, so the main idea is this.
So similar to Spartan, in Spartan we need the 2 rounds,
Yes.
and for 1 round we vary it with some random point, and we do sum check for first round. For second round, we do the sum check proportional to the number of the matrices again, number of the matrices.
Yeah, kind of. So yeah, there's also again similar to Spartan. We have first sum check, and then we have another sum check here, and we have to open like on each matrix. We have to open at random AY. Yeah. So it's exactly same as Spartan, but just generalized over multiple metrics. So yeah, with this, they complain that it is the first snark for air constraint. Yeah.
First what? First
Snark for air constraints. But I mean, there is also Starks, but I guess they mean like it doesn't use Fry. There's no entity. Yep. That's it. So I tried to be start from the high level. Yeah. It was good. Yeah.
Yeah, I feel that. Like, thanks for that.